This video covers the exponent laws from Algebra 1 that are needed to help simplify expressions with rational exponents. Or in other words, exponents that are fractions. When I talk about rational exponents, we're talking about exponents that are fractions. Before we begin, it is very important that you have the prerequisite skills needed, and these bellwork questions will suffice as a test of your current knowledge before we go ahead and begin the actual lesson. I will go over these with you, but if you are unable to complete these problems and understand my explanation, please go back to the previous video and re-watch those examples. I'm not going to go into as much depth with these as I did in the previous video, so please take your time and give them a shot. All right, go ahead and pause, and I'll give you a moment to do that and give these a shot. And okay, let's go ahead by quickly going over these bellwork problems. So in number 1, we're trying to find the cube root of 16 times x to the 9th power. And you would have to first know that 16 is really 8 times 2 because 8 is a perfect cube and 8 times 2 is 16. We would not want to use 4 times 4 because 4 times 4 are 4 and 4 are perfect squares. They are not perfect cubes. So you take the cube root of 8 times 2, and then the x to the 9th power is going to be split into 3 groupings of x cubed, because again, we are trying to find the cube root, so we want groupings of 3 of these. And it just so happens we have 3 groupings of 3. So you can cancel out the cube root of 8, and that will give you 2, because the cube root of 8 is 2. 2 to the 3rd power is 8, because 2 times 2 times 2 is 8. And then the x cubes, there were 3 of them that got canceled out. So all 3 of them are going to come out as an x cubed. And then the leftover 2 that is still under the cube root sign just tags along for the final answer. And there you have it with number 1. Now in number 2, we have to simplify and then rewrite into radical form. And notice that right now these are in exponential form with rational exponents. There's that big word again. I'll go ahead and write it out because it's really important. Rational exponents. And rational exponents are just exponents that are fractions. The 3 that you see right up here, that is, I guess technically it's a rational exponent because you could make it into 3 over 1, and now it is a fraction, but it's a whole number, nice and friendly and familiar to you. But when we talk about rational exponents with Algebra 2, then that means we are talking about exponents that are fractions like 3/4 and 1/5, and we have to simplify them. So let's go ahead and do that. Let me just back up this work. Okay, so the first thing to notice is because we are multiplying these together, we are going to be adding the exponents. That is just the exponent law of whenever you are multiplying 2 variables with the same base, then you just add the exponents together. 2 plus 5 is 7, so you would have x to the 7th power. But over here, let's just add 3/4 and 1/5. We need a common denominator to do that, and that denominator would be 20. So we will multiply by 5s and 4s, and we're going to get 15 over 20 plus 4 over 20. And then adding the numerators together, 15 and 4 is going to give us 19. So the new expression is going to say x to the power of 19 over 20, but do notice we are converting this into radical form. So we need to remember that when you have exponential form and we need to turn things into radical form, we need to remember power over root. Power over root. The rational exponent, the numerator, is going to become the power when you rewrite it into radical form. So the 19 is going to be the only exponent you see on the variable x, and then the 20 is going to become the root, written in the root position. So you would say this as the 20th root of x to the 19th power. And that is that for the bellwork. If you were able to follow along, great. Then let's go ahead and get into the notes. And if not, please pause, rewind, maybe listen to it again, or go to the previous video, which does have examples that are in this fashion. So let's go ahead and jump to the actual notes. Take a moment to pause the video and set up these notes and give yourself some space to write out the answers and just basically mark things up as we work out the problem. So I'll give you a moment to do that now. And okay, here we go with the first lesson of radical expressions, equations, and functions. So we are just going to be getting into the exponent laws as they pertain to the problems we're going to be doing in the later lessons. So let's talk about the exponent laws. And I certainly hope that a lot of this you recall from Algebra 1 because it is just the same rules with a little bit of an Algebra 2 twist. So the first thing to notice, the word rational, it means what you are writing could be expressed as a fraction. So that's why we have rational exponents. Take a look at the first example you see there. This is called the power rule, and you can see that name for it right over there. The power rule is the rule that says if you have a variable that is currently being raised to an exponent, and then the entire expression is then being raised to another exponent, then you just multiply those exponents together. And instead of the word exponent, I could say the word power. If you have a power being raised to another power, so the power of 2 is being raised to the power of 3, then just take those two powers and you multiply them together, and that would be the only power that you would need to write down on the final expression. So that's why you see an a to the 6th power written right there. Now take a look at the first example. It is asking you to test your knowledge of that rule by basically working backwards. I'll pause for a moment and maybe try to see if you can figure out what is the value for f that makes this statement, true. And just kind of look, you have an 18 there, you have that positioning there. I'll give you a moment to think. Okay, so if the power is supposed to be 18, and then on the other side of the equation, you have the power rule happening. Well, notice that f and that 3, you have the power of f being raised to the 3rd power. Since the power rule says you can multiply those together, the result is supposed to be 18. So 18 is going to equal 3 times f. Divide both sides by 3 to cancel it out, and 18 divided by 3 is going to give you 6. So that means f equals 6, and that was the answer to example 1. Let's take a look at example 2 now. This is another rule. Got to erase all of that. Okay. This is the rule that can just be thought of as the same base dividing rule. And you will notice in the example, we have an a to the 15th power is being divided by an a cubed. So another way of thinking about that would be writing it as a fraction, just like that. And because we are dividing, that actually means you're going to be subtracting the exponents. So again, you have a and a. It's the same base. That's why it's called the same base dividing rule. Because we are dividing these, you are going to take those exponents and you are going to just subtract them. So 15 minus 3 is going to be 12, and that is why you see an a to the 12th power written down as that answer. So let's test that with the next example. Only instead of keeping it as whole numbers, we have fractions, rational exponents. Again, 17 over 9 is a rational exponent, but it's the same law from Algebra 1 that we're about to apply here. Just take a look though. The answer is apparently written in radical form, and we are trying to figure out the value of x. Little tricky problem in some regards, but maybe go ahead and pause the video and see if maybe you can get things started by taking the same base dividing rule and applying it to what I just bubbled in purple. I'll give you a moment to pause and get it started, and resume when you're ready. Okay, so let's talk about what to do in this problem. We clearly need to put things into radical form, and right now we have things in exponential form. So let's go ahead and apply the same base dividing rule so that we can take a fraction, or these two 4s, and write them as 1. So you are dividing, and that means by the same base dividing rule, you are going to be subtracting your exponents of 17 over 9 and you're subtracting 11 over 9. And since the denominators are already the same, they're already 9, you can just do 17 minus 11, which is going to give you 6. Now, since 6 over 9 can be reduced, since it's a fraction, you can simplify by a factor of 3. We can divide both 6 and 9 by 3 and get 2/3. So that is going to be the new rational exponent on the number 4. 4 to the power of 17 over 9 divided by 4 to the power of 11 over 9 is going to become 4 to the power of 2 over 3. We have now applied the same base dividing rule, and we can see that the answer is supposed to be in radical form. So now that we have rewritten the problem in exponential form with just one base, we can now use power over root. So let's go ahead and put a P for power and an R for root. 2 is going to be the power on the number 4, and then 3 is going to be the root. And now take a look at the answer. So it's supposed to have the cube root, which we have, and then x is in the same position as the number 2. So that means x is going to equal 2, and now we have the answer. So just to recap, the algebra 1 concept of this is just doing the same base dividing rule, which you saw as the example that I'm bubbling in right here. That's the algebra 1 way of looking at this. The algebra 2 way of looking at it is instead of having 15 and 3, some nice friendly whole numbers, you now have fractions that are your exponents instead. And when you do the same base dividing rule, you're now just subtracting fractions instead of whole numbers. But, that's still an algebra 1 concept. You have a common denominator already, so you don't have to do any extra work there. And after subtracting the numerators, you just had to do a little of simplifying by dividing by 3. So let's look at a few more examples and then a little bit of practice. Take a look at examples 3 and 4. Maybe pause the video and just set them up. Let's talk about these in a moment. Give you a moment to pause. And okay, here we go with number 3. So this is called the multiplying radicals rule. Very easy one to keep in mind. If you are multiplying two radicals together, or two separate radicals together, then you can quite literally just multiply the exact same numbers together under one radical sign. So you can see that first example right here. It is just the square root of 2 times the square root of 2, and that would be equal to the square root of 2 times 2. And since 2 times 2 is 4, you would have the square root of 4. Now, in that particular case, though, the square root of 4, well, since that's a perfect square, it would go back to being 2, and that would be the final answer in that case. But just to further the point along, and so you can test yourself, let's say we have a square root of 14 times the square root of, 3. I'll give you a moment to think about that. What would that result be? And here we go. So the square root of 14 times 3, or the square root of 14 times the square root of 3 is the same thing as the square root of 14 times 3. And since 14 times 3 is, what is that? That is 42. You would have the square root of 42, and that's not a perfect square. And there's no perfect square that can simplify it. So that would be your answer in that case. This is just the multiplying radicals rule. Just straight up multiply the two things together that are under radical signs and stick them under one radical sign. The same thing would kind of happen if you had variables. So if it was an A and a B, then those A's and B's with the 14 and the 3 would just tag along, and there would be an AB underneath that last part of the problem. Multiplying radicals, third rule. And the fourth rule, the same base multiplying rule. You have likely seen this many times, and I'm pretty sure I talked about it in the previous video. Basically, when you are multiplying two bases that are exactly the same, just take those exponents and add them together. You can see right here that 7 and 4 make 11, and since we were doing a to the 7th times a to the 4th, you would just do a to the 7 plus 4th power, and 7 plus 4 would be 11. So take a look at the next example, maybe give it a shot. Notice you now have rational Exponents again. Rational exponents, for those of us who are forgetting that very important vocabulary word. Rational exponents are just your exponents that are fractions that you have a numerator and denominator with. So that example, take a moment to give it a shot. I'll pause and okay, let's now do it. So you are multiplying 6 to the power of 9 over 2 times 6 to the power of negative 5 over 2. You're just going to add those two fractions together using the same base multiplying rule. 9 over 2, we're going to add negative 5 over 2. And that, since you already have a common denominator of 2, you can just do 9 plus negative 5, and that's going to give you 4. And since 4 over 2 can be reduced to 2, then we have to simplify our fraction. And then 6 is the base. The power is now 2. You could leave your answer like 6 squared, but if it's something that you could simplify, in this case, you could make it 36, then that is what you would have to do to finish it up. That was number 4. I think there is one or two more on the next slide. Yes, the last example, and we'll practice it twice. So one of the trickier exponent laws is the negative exponent flip and switch rule. I'm going to draw it. You can see it right there. Maybe pause the video and set up these examples, and then we'll come back in a moment. So go ahead and pause. Okay, here's the quick explanation of the negative exponent flip and switch rule. Let's say you have a fraction that looks like this, and let's just give the x a square, and well, that 3 has a power of 1. You have positive exponents. You are going to leave everything where it is and not do anything to this problem. The final answer would be x squared over 3 because both of those exponents are positive. So you don't move anything and there is nothing to simplify. Now, if I were to go ahead and make that x squared, that 2 a negative 2 and that 3 a negative, or the exponent of 1 is now going to become negative. Now we have to use the negative exponent flip and switch rule. And it's very simple. Whatever has a negative exponent, you have to flip that expression or that variable or number, you have to flip it to the other area of the fraction that it's not on, and then you have to make its exponent positive. So basically that means this x, because it's in the numerator, it's going to flip to the denominator, and you're going to switch its exponent to positive 2. Likewise, the 3 was in the denominator with a negative exponent. It is going to flip to the numerator, and the negative 1 is going to become positive 1. So now that we have flipped and switched the exponents, we have the final answer. This is the simplified version of what you have here. Another way this could have been written, by the way, if it said x with a 3 and maybe negative 3. Or let's go 2 so the math stays nice and simple. Here's another way of thinking about this idea. So now you have the entire fraction and there's a negative exponent right there. Well, the negative exponent would multiply to both of those exponents right there. And that would give you an x to the negative 2 and a 3 to the negative 2. I know the 3 had a 1 as its exponent before, but whatever, just go with this. So now that both of those exponents have been sort of distributed, you can now see that the denominator, you have a 3 with a power of negative 2. That's going to flip to the numerator, and then you switch the negative 2 to positive, and then the x with the negative 2 is going to flip to the denominator, and then the negative 2 is going to also become positive. So it's just another way of looking at the same style of problem. One more piece to it, and then we'll just do the 2 examples you see right here. Let's say you had an x with a negative 4, and in the denominator, let's go with a y squared. So in this case, the y squared, that exponent is positive. It's not going to move the y squared anyway. That stays exactly where it is. But because you have an x with a negative 4, it's going to have to flip to the denominator, and then that negative 4 is going to switch to a positive 4. And you might be asking yourself, well, what goes in the numerator? I thought something has to flip up there. Doesn't the y flip up there? No, you don't touch the y. It had a positive 2. There was a number 1 in front of that x that did not have to be written there, but once you move the x out of the numerator, the number 1 is the only thing that is left over. So you would have a 1 in the numerator, and then the y squared x to the 4th would be in the denominator. Likewise, if let's just say there were a z to the 3rd power in the numerator, well, since the z had a positive exponent, it would stay in the numerator and it would not flip anywhere. So you can see the only thing in this example, now that it's set up kind of in its full fashion, the only thing that moves is that x to the negative 4th power, because that is where the negative exponent was, and it flips to the denominator. All right, enough rambling about that. Let's do these two examples. So in this example, which is a little trickier, on the trickier side, let's go ahead and learn about how to approach something like this. Work from the inside out. Don't be intimidated by that cubed root symbol. Work from the inside out. If you see a negative exponent, you're not done working with the inside of the problem. So there's more to do here. Let's just go ahead and extract the 9 with the 3 to the negative 1st power. And, oh, got little stray marks right there. Let me just clean those up. All right, ignore the cube root. Let's simplify what you see right here. This number 9 has a positive 1 as its exponent, and the 3 has a negative 1. Well, I just explained at length. If the exponent's negative, it is going to flip and switch. So the 9 has a positive 1. It's not going anywhere. It's staying in the numerator. The 3 has a negative 1 as its exponent, so it's going to flip to the numerator. And since there was already a 9 up there, it's going to multiply with that 9. That will always happen. Always multiply if there was a number or variable already in that position when you move something there. And then the exponent of negative 1 becomes positive 1. Since there is nothing left in the denominator, there was actually a 1 in front of that 3. But 9 times 3 is 27, and then 27 over 1 is just 27. So working from the inside out sometimes makes the problem look a lot easier, because now that we have taken care of what was under the radical sign, we can now see that we are just finding the cube root of 27. And you should know your perfect cubes, and that 27 is a perfect cube, and the cube root of it is just the number 3. So that is the answer to number 5. It is 3. And let's quickly talk about number 6. So here's another way to approach a question like this. There are multiple ways of doing it. I'm just going to show you one way that uses this exponent law, and then we'll just do some practice problems on the next slide. So you're going to notice that we have in the numerator, you have a normal setup where those two fractions or those two expressions are being multiplied together, and we're going to ultimately add them. Here's another way I want you to think about this. Let's just go ahead and rewrite this problem moving the 8 to the power of 2 over 4 to the numerator. Write this down with me, or at least look carefully and just try to understand how the negative exponent law is going to work in this case. So I'm going to bring the 8 with the 9 over 4 over. We are multiplying by 8 to the 3/4 power. And then we are moving the 2/4 from the denominator to the numerator. And since there was already terms up there, we're going to be multiplying, and we're going to multiply by 8. But since we are moving the entire thing from the denominator to the numerator, you are basically doing the negative exponent rule backwards. You're undoing it. We are moving something. We are flipping something from the denominator to the numerator, so that means we have to switch its exponent. So we're going to make this into a negative 2 over 4. And then now the denominator would just be a 1 because there is now nothing left in the denominator. And you can see that this problem is now just a same base multiplying rule where you are taking 9/4 and you are adding 3/4 and then plus negative 2/4. Ooh, a lot of stray marks there. And adding these is pretty easy to do. You have this common denominator already set up with a 4, so just add 9 and 3, that's 12. 12 minus 2, that's going to be 10. And then 10 over 4 reduces to 5 over 2. So you have 8 to the power of 5 over 2 as your final answer. There were a few ways of doing that problem. You could have done the same base multiplying rule to the 9 over 4 and the 3 over 4, and then you could have just subtracted the 2/4. But I want to highlight the idea that just because the denominator had an 8 to the 2/4 and it was positive, you could flip it from the denominator to the numerator and make the 2/4 negative. It's just another way to illustrate this procedure. All right, on the last slide, I've been making this video long enough. We have some practice problems here. I will give you a moment to pause and attempt them, and then I will quickly flash the answers, and then we'll call it quits with this video. So what you can observe at the top before you get started, just a quick review. Writing from exponential form into radical form, very important skill. Going from radical form back into exponential form, also important. And then you're going to notice there's a couple ways of representing the square root, which you've seen a few times now, but the root being 2, you never have to write that there. So you're never going to really see the root of 2 written in that position. You just have to know that when nothing is in the radical sign, that it's always a 2 in that spot by default. Taking a look at the examples down here, you have the questions 1, 2, 3, and 4, and then what you would first do is apply the exponent law to rewrite that question using the exponent law, and then converting it into radical form at the end. So I'll give you a moment to pause and give it a shot, and then we will do these together. And all right, number 1. So because you are multiplying, you're going to have to add those exponents together. Negative 11 plus 4 is going to be negative 7. So you would have 3 to the negative 7 over 2 power. And then rewriting this, I mean, if you got that far, that's pretty good. And rewriting it into radical form, you would have the power being negative 7 and then the root being 2. So you would have the square root of what you see in red, the square root of 3 to the power of negative 7. Now, if you got that far, that's really good. But you could also go a little farther by remembering that since you have a negative exponent, you can go a little bit further to make it no longer negative. And you could put a 1 underneath the 3, and then flip the 3 to the negative 7th to the denominator and make that 7 positive. And then the answer would actually come out like this. So 1 over the square root of 3 to the 7th power. But again, if you only got as far as what is written in red, very good job. Number 2, you have the same base dividing rule, sorry. And when you are subtracting 10 over 7 minus 8 over 7, you are left with 2 over 7. Putting that into power over root, rewriting it into radical form, you would have the 7th root of 4 squared. And if you made that into the 7th root of 16, that would also be a good answer. The third example is the power rule. So you would be changing that 3 into a 3 over 1. And then the power rule says you just multiply those powers straight across. 3 times 5 is 15. 1 times 2 is 2. So you have 5 to the power of 15 over 2. Putting that into radical form, you would have the square root of 5 to the 15th power, which is some gigantic number. Don't even worry about it. And then the last example, you are multiplying all of those together, so you will be adding all of the exponents together. And when you do that correctly, you will have 17 over 12, and putting that into radical form, the 12th root of 2 to the 17th power. Thank you for following along with the video and all of the examples. Hope things helped, and I will see you in the next one.